Good afternoon. This is the Combined Science Trilogy paper for physics. So always start off by writing your name. There are different types of electromagnetic waves. What do all electromagnetic waves transfer? Waves transfer energy without transferring matter. So all waves transfer energy. They never transfer matter. Charge and sound are not one of the correct options. Question 1.2. Complete the sentence. Choose the answers from the box. Different types of electromagnetic waves have a different something and a different something. Since we're talking about electromagnetic waves, charge does not come into it. Frequency, speed, and wavelength do come into it, but since electromagnetic waves are being discussed, they have a speed of 3 times 10 to the 8 meters per second, and all electromagnetic waves have that speed. So that's not it. And then frequency, and wavelength are our answers. So different types of electromagnetic waves have a different frequency and a different wavelength. It doesn't matter which order it's round in. Next, we have figure 1, which shows an electromagnetic spectrum: radio waves, microwaves, infrared, something, ultraviolet, X-rays, and then something else. We have to get this right in the right order. Thankfully, I have a mnemonic to remember the order of the electromagnetic spectrum, which is red Martians invade Venus using X-ray guns. So I'm just writing the first letter out of the electromagnetic wave. V stands for visible light, and G stands for gamma rays. Obviously, learning the mnemonic is not just enough. You have to remember what the electromagnetic spectrum is. 1.4. Different electromagnetic waves have different uses. Draw one line from each type of electromagnetic wave to its use. Let's have a look. Microwaves, ultraviolet, and X-rays. Let's see which one we can do first. Electrical heaters, energy efficient lamps, imaging bones, we know that is X-rays. Satellite communications, we know that is microwaves. Your phones use microwaves. And ultraviolet is energy efficient lamps. Electrical heaters, if they said infrared, then I would be thinking electrical heaters. Question 2. Student investigated how the color of the surface affects the power of the infrared radiation emitted by the surface. The infrared radiator measures the power of the infrared radiation emitted by the flasks. Okay, and these are the two flasks and the kettle, infrared detector, thermometers, measuring cylinder. He's got all the works. The question is, the student poured hot water into each flask. What should the student do to reduce the risk of burning herself with the hot water? She should be sensible. All right, she should follow every instruction that Mr. Valuran has ever given her. When it comes to doing practicals in his lab, for example, she should stand up. That's important. She might use a funnel to pour the hot water into the flask. She might be very, very clever and allow somebody who knows how to do it properly to pour it, and she will try her best not to touch the hot surface. All right. But one of the best things she could do, if she has access to it, is that she probably won't. She could wear heat-proof gloves. Although I don't think anyone has used heat-proof gloves in our school to do practicals. Your teacher might, but you won't. If you put gloves on its own, you don't get the mark. Heat-proof gloves, but all of these things should give you, well, any of these things should give you the mark. Describe how the student would use the equipment in figure 2. Now we're using all of the equipment in figure 2 to compare the power of the infrared radiation emitted by each surface. So we've already been told that the infrared detector is used to measure the power of the infrared radiation. All surfaces emit infrared radiation. Some surfaces emit more. If you are hotter, you'll emit more. So what we want to do is heat up these surfaces and see how much infrared radiation they emit. And that way we'll be able to know which one emits more infrared radiation. To heat up the surfaces, what we actually do is boil water in the kettle. So that's the first thing that we're going to do. Water in kettle. And then we'll use a measuring cylinder to pour the same volume of water. Measuring cylinder measures volume. All right. Measure same volume of water into each flask. So each conical flask gets the same volume of water. Okay, so we've poured it into both of those flasks. Then using the thermometers, use thermometers to measure temperature of each flask. And what do we need to do with the temperature? We need to make sure that they're the same temperature. And finally, use infrared set detector to measure power of infrared emitted by each surface. Okay, so what are the things that we're keeping the same? We're keeping the volume the same. Of course we're doing that. We're keeping the temperature of the water in the flasks the same. Yeah, and we're boiling it in the same kettle, if that matters. So we've done everything we can. Student investigated how the power of the infrared radiation emitted from a flask changed with time. The table shows the results. Time in seconds increasing in 60 seconds each interval, and the power in watts clearly decreasing. So that's the first thing that you write. As time increases, power decreases. Okay, then obviously because it's 2 marks, we can't leave it there. There has to be something more. Let's see, from 0 to 60 seconds, it's a decrease of 0.8. From 60 to 120, it's a decrease of 0.7. From that to that is a decrease of 0.6. From that to that is a decrease of 0.5. That to that is 0.4. That to that is 0.3. That to that is 0.2. So clearly, as time increases, the rate at which the power decreases is going down. So rate of decrease changes, decreases. I'll tell you now, if you figure out the last question, this is going to be really easy. What is the most likely value for the power of the infrared radiation emitted after 480 seconds? So up to here, we discovered that each time the decreases. So from here to here is 0.8, then 0.7, then 0.6, then that was 0.7, 0.6, then 0.5, then 0.4, then 0.3, then 0.2, well, 0.2 here. From 4.7 to 4.5 was a decrease of 0.2. If that trend was to carry on, then from here to here, it should be a decrease of 0.1. So what would that value be? It would be 4.4. At 480 seconds, it should be 4.4. Next. So in this diagram, you've seen a Leslie cube to test how different surfaces emit different amounts of infrared radiation. This is the practical that we've done in school. And figure 3 shows the infrared detector a distance away from the Leslie cube, and it's filled with hot water. and it's asking, give one advantage of using Leslie cube rather than the equipment and the setup that we used in figure 4. Figure 2 a couple of pages ago. So the question really is why is this a better test? Well, this has 1, 2, 3, 4 sides instead of 2, so you can test more sides, and I'm going to tell you all the correct answers. Test more surfaces. What's another advantage? Well, the water inside the Leslie cube does not need to be measured. No need to measure volume of water. Why is that? Because we don't need to try and keep it a fair test, because all the surfaces is heated by the same hot water. So therefore, we don't need to no need to measure temperature. The reason why we measured the temperature in the previous test was so that if both the surfaces are heated up by the same temperature water, then we can say it's a fair test. Well, all surfaces are going to be heated up by the same temperature water, so it's definitely going to be a fair test. That's it. So all of these reasons make the Leslie cube setup a much better one. The teacher improved the demonstration by using 4 infrared detectors connected to a data logger on a computer. Each detector was pointed at a different surface of the Leslie cube. The distance between the surface and the detector was the same in each case. Give 2 reasons why this improved the demonstration. There's many reasons why, but let's think about it. If the Leslie cube is right in the middle and there's 4 detectors on each side and a computer is taking the measurements, then you can take all the measurements at the same time. You don't have to move the cube, and therefore the results will be more accurate. So you can take more measurements, all the measurements at the same time. No need to move the cube. Results will be more accurate. So that's what we're going to write down. Take all measurements at the same time. Therefore, no need to move the cube. And results will be more accurate. Next question. Figure 4 shows an apple hanging from a tree. X marks the center of mass of the apple. So the question is, draw an arrow on figure 4 to represent the weight of the apple. The weight of the apple acts down like that. It should be a straight arrow down. Next question. Fantastic, a maths question. The apple has a mass of 0.150 kilograms, gravitational field strength obviously 9.8 newtons per kilogram. Calculate the weight of the apple, and because they're very nice, they've given us the actual equation, and all we have to do is substitute and then compute. So weight equals mass times gravitational field strength. Well, what's our mass? Our mass is 0.150. So weight, which is going to be W, is equal to 0.150 times by gravitational field strength. What is that? Which is 9.8 times by 9.8. So because there's no rearranging to do, just type it into our calculator, and our answer happens to be 1.47. 1.47 is our answer. Bingo. 2 marks. Next question, 3.3. The apple in figure 4 is stationary. It's not moving. So why is the apple stationary? The apple is stationary even with a weight on it, is because there must be something holding it up, which is the tension from the stem, isn't it? And if this and this are the same as each other, then we have a resultant force which is equal to 0. The apple is stationary because the resultant force on the apple is 0. When the apple is ripe, it falls from the tree and accelerates towards the ground. Why does the apple accelerate? So now the tension is gone because it's not being held up by the tree anymore. There's only one force on it, and therefore if there is a resultant force which is acting down, all right, it is going to accelerate it. The resultant force on the apple is downwards. That's why it accelerates downwards. Next question. The acceleration of the apple is 9.8 meters per second squared. Which is the same as our gravity, but we'll talk about that in a second. The velocity of the apple changes from 0 to 4.9. That's our change in velocity. Okay, calculate the time taken for the apple to fall to the ground. That little triangle V is that, by the way, change in velocity. Calculate the time taken for the apple to fall to the ground. This again is a plug the numbers in type of questions. There's nothing else that we need to do. We need to say the time taken, t, is equal to change in velocity. Going from 0 to 4.9, what's the change? The change is 4.9 meters per second divided by our acceleration right there is 9.8. 4.9 divided by 9.8. I need my calculator for that. Hold on a second. .9 divided by 9.8. I feel a little bit embarrassed because I used my calculator for it. I should have known it's 0.5 seconds. There we go. Next. Figure 5 shows a compass, like a plotting compass, and it's got a arrowhead pointing to the north and obviously from the south. Why does the compass always point in the same direction when it's not near a magnet? Why is that? Well, a compass, what's it used for mainly? It's used for plotting courses, isn't it? Because the Earth has its own magnetic field. Our compass points to the magnetic north of the Earth, which happens to be, the magnetic south of the Earth, which happens to be the North Pole. All right, because the Earth has a magnetic field. What material could the needle of the compass be made from? Well, this is just a recollection of what material is magnetic. Is aluminium magnetic? No. Is copper magnetic? No. Plastic? Definitely not. Steel? Yes. Figure 6 shows a coil of wire. There is a current in the coil. The circles show the position of 4 compasses. All right, so there's 4 compasses put on the circle. Excuse this section because I think what I've done is I've pasted that question over it. Anyway, it should be a circle. Which statement describes the magnetic field around the coil? The field has the same strength at all points. Well, if that were true, then there should be the same number of lines everywhere, but there isn't. Here there's fewer lines than there are here, so that's not true. The field is stronger further away from the coil. That's definitely not true. You can see the lines get closer together the closer you get. The field is the strongest at the ends of the coil, here and here. That is definitely true. Then it says draw one arrow in each circle on figure 6 to show the direction of the magnetic field. One arrow in each circle to show the direction of the magnetic field. The magnetic field goes from the north to the south. So from the north to the south, from the north to the south, from the north to the south, from the north to the south. Now, why have I drawn this arrow to the left instead of drawing it inwards to the south? Well, this, if you imagine it, if you follow this imaginary line along like that, I'm imagining it going back around like that, so that's why I've drawn it out like so. Give 2 ways a magnetic field around a coil could be made stronger. What are the 2 ways the magnetic field around a coil how can be made stronger? There's 2 ways. You see these plus and the minus, well, that shows that there is electricity passing in that coil of wire. There's current in that wire. If I increase the current, all right, there's going to be a stronger magnetic field. Or what I could do is, if you remember the practical from school, you could just put a iron nail in it, which is introducing an iron core. Insert an iron core, which basically channels the magnetic field, makes it stronger. I could also just increase the number of coils, increase the coils, or the number of coils. That should do the trick as well. All right, 5.1. The stopping distance of a car is the sum of the thinking distance and the braking distance. Which factor affects the thinking distance? How well the driver thinks. That's what we're talking about. Does the condition of the tires affect the driver's thinking, his brain? Absolutely not. Does driving on wet roads affect his brain? No. Mass of the car? No. The tiredness? Yes. Using a mobile phone? Yes, because it's a distraction. Explain why a person should not drink alcohol then drive. Because it's not cool, guys. Anyway, but the reason is alcohol is a depressant. It slows down your reaction time. Slows down your reaction speed, which means increases the reaction time. Therefore, if you take longer to think, your thinking distance increases, which is the time while you're thinking the car is still moving forward. That's your thinking distance. That increases, so you're more likely to have a collision. So to get those 3 marks, you need to get those 3 points down. It increases a person's reaction time. If their reaction time increases, it increases thinking distance. And if the time or if the distance while they're thinking increases, they could have a crash, more likely. So more likely to have a collision. All right. Oops. Collision doesn't have 2 S's. Collision. Next. Quick question change. The highway code gives information on how thinking distance depends on the speed of the car. Remember, the thinking distance is the distance the car moves while the person is reacting to the danger. So, but the speed of the car doesn't affect somebody's thinking time. It only affects somebody's thinking distance, because while they're thinking, the car is still moving forward. If the car was moving fast in the first place, while they're thinking, the car would have moved forward an even longer distance. That's the information that's shown on the graph. What is the speed of a car if the thinking distance is 16 meters? Well, if the thinking distance was 16 meters, which is right there, remember it goes up in ones for every tiny square, the speed of the car can be measured or found out by doing that. All right, putting your ruler again, all the way until the line, and then drawing a line down. So that is 21, 22, 23. Describe the relationship between the speed and the thinking distance. That's very easy. As the speed increases, the thinking distance increases, but it's a straight line, so it's a directly proportional relationship. The highway code assumes that this driver has a reaction time of 0.7 seconds. Draw a line on figure 7 to show the relationship of a driver with a reaction time of 1.4 seconds. Oh, this is really good. So I'm just going to use a different color. 0.7 seconds, double the reaction time to 1.4 seconds. That means your thinking distance will double for every increase in speed of the car. So what does that mean for us? Well, if the speed of the car was 5 meters per second, for 0.7 seconds it's 3.5, but for 1.4 seconds, it's double 3.5, which is 7, right there. Now, for 10 meters per second, for 0.7 second reaction time, it's 7, but double that for 1.4 and it becomes 14. For 15 meters per second, it's 10.5 seconds for 0.7, double that for 1.4, 10.5 doubled is 21. Okay, now I don't need to do another plot. All I need to do is use my ruler, join up those lines, and that is the line that we get for a reaction time that's doubled. Okay, the question is, the car accelerates at 5 meters per second squared over a distance of 45 meters. The initial velocity of the car is 0 meters per second. To calculate the final velocity of the car, use the equation sheet to give your answer to two significant figures. I can see the equation sheet, and it says final velocity squared, final velocity squared minus initial velocity squared is equal to 2 times acceleration times by distance. Okay, this equation ticks off everything that we need. Distance, right here. But I'll underline it in a different color. There you go. And then acceleration, right there. And then initial velocity, right there. And then final velocity is what we're trying to calculate. So, final velocity squared. Final velocity has the symbol v. Initial velocity has the symbol u. Acceleration always has the symbol a. Distance is a funny one because it doesn't have any of those symbols. It has a symbol s. Okay, so then we can recreate that equation by writing v squared minus u squared is equal to 2 times by a times by s. And we can plug in our numbers or substitute. Right, v squared remains the same, v squared minus 0 squared. Well, that cancels out immediately, doesn't it? Is equal to 2 times acceleration of 5 times by s, which is 45. We don't know what v squared is, we're trying to calculate that. So v squared is equal to 2 times, well, what is 45 times by, well, 2 times by 5 times by 45. 2 times by 5 times by 45. 2 times 5 is 10 times 45 is 450. Just to check, I'm going to plug it into the calculator, and there we go. 450 is the answer. So v squared is 450. So how do we get v on its own? To get v on its own, you need to do the opposite of squaring, which is square rooting. If I square root this side, then I have to square root this side. So v is equal to the square root of 450. The square root of 450 is 21.2132. Okay, now does it ask for any significant figures? Let's have a look. Yeah, it does. It asks for two significant figures. 1, 2. We don't need any of those things, and we don't need to round up because 2 is smaller. This 2 is smaller than 5, so 21 is your answer. Bingo. Figure 8 shows a longitudinal wave. What do labels A and B on figure 8 represent? So A represents where the particles are spread out, and B represents the distance between where the particles are squished together here and the next point where the particles are squished together. So A represents rarefaction. Rarefaction. That's where the particles are spread out. This point where the particles are squished together is called compression. So B represents the distance between the midpoint of the compressions. Actually, what B actually represents is the distance of one wave, or the length of one wave, which is a wavelength. Next one. So the next question asks, the wave shown in figure 8 has a frequency of 4 kilohertz. All right, so that's frequency. And kilo means 1,000 times by 1,000. Calculate the period of the wave. Use the equation sheet. The equation sheet that we need is the equation sheet. What it will tell you is something like this. Period is equal to 1 divided by frequency. And that's all you need to do. But because we need to do a conversion, that's the first thing that we need to write down. Frequency is equal to 4 kilohertz, which is equal to 4,000 hertz. So now, once we've converted, we're ready to put our numbers into the equation. Period is equal to 1 divided by 4,000. And if you're like me, I can't do 1 divided by 4,000 in my head. It is 0.00025. Is that right? 0.00025. Okay. And what's the units for period? Well, period is actually a time. It's called a time period. So the unit is seconds. Now, the answer that you might get in your calculator might look like this. 2.5 times 10 to the minus 4. How do I convert that to 0.00025? Well, we don't need to, but if we did, what we would do is write 2.5, and then take the decimal place back 1, 2, 3, 4 spots and put it there. And then for the rest of the places, we'll add the zeros. There we go. 0.00025. Sound waves are longitudinal, it says. Figure 9 shows the speed of sound varies with the temperature of the air. So if the temperature of the air is increased, the speed of the sound also increases, it seems, because it shows a graph going up like that. Use the physics equation sheet to answer the questions 6.3 and 6.4. Write down the equation that links frequency, wavelength, and speed. That is V equals F times lambda. Lambda is that simple because wave speed is equal to frequency times by wave length. Just as easy as that. A sound wave with a frequency of 300 hertz travels through the air. The air has a temperature of 28 degrees Celsius. Determine the wavelength of the sound wave. So that is our frequency, F, and we just need to find the wave speed from the graph. at the temperature of 28 degrees. So it seems that between 0 and 10 there's 5 squares, so each square represents 2 degrees. So 28 will be 22, 24, 26, 28. 28 is right there. Using a ruler, straight line all the way to there, then finding that ruler and moving all the way. Oops, that's not a straight line. There we go. So it ends up here. Between 45 and 50 there's 5 squares, so each square on this side goes up in ones. 45 to 46 to 47 to 48. So 348 is our wave speed. 348 then, oops, v equals 348. 348 then equals, okay, frequency, which is 300 times by wavelength, and the symbol for wavelength is lambda, upside down y. Next, to get lambda on its own, you need to do 348 divided by 300. So let's pause for a moment and think why I have done that. All right, to get lambda on its own, or wavelength on its own, I need to get rid of the 300. Currently the 300 is timesing onto the lambda, so to get rid of it I just need to divide it. All right, divide by 300 on this side. All right, these two cancel out now. Okay, but if I divide by 300 on this side, I have to divide by 300 on this side, which is what we've rewritten as wavelength is equal to 348 divided by 300. Finally, all you have to do is put those numbers into the calculator. 348 divided by 300 is equal to 1.16, and wavelength is measured in meters. Okay, superb. Next question, final question, is a very easy, quick paper. So in question 7, it asks, it's figure 10 shows competitors in the wheelchair race at the London Marathon. There's a wheelchair section of the London Marathon. The distance of the London Marathon is 42,000 meters. Use the physics equation sheet to answer questions 7.1 and 7.2. 7.1 says, write down the equation that links distance, force, and work done. When we look at our equation sheet, there is one equation that talks about work done, force, and distance, and that is work done is equal to force times by distance. Remember, from the previous questions, we know distance is S, force is F, work done is W. So, during the race, competitors work against air resistance, obviously. The work done against air resistance by the winner of the race was 3,360,000 joules. Oh, that's a lot of joules. Calculate the average air resistance acting on the winner of the race. So we know what the work done is. We know we want to find out the force of air resistance. All right. So what other numbers do we need if we were to use this equation at the top? Well, the other number that we would need is distance. And do we know what the distance is? Yes, it's right here. It's 42,000 meters. So 3,360,000 is equal to force, which is the air resistance, times by the distance, which is 42,000. Okay, that's it. I can then rewrite it. Remember, rearranging the equation is a skill that we all need to learn. If F is being times by 42,000 on this side, and I want to get rid of it so I can get F on its own, or make F the subject of this equation, I just divide by 42,000. If I do that on this side, then I need to do it on this side. So I have f, which is the subject. I'll rewrite that actually. F, which is the subject, is equal to 3360000 divided by 42000. Right. I could just plug that in into my calculator and I'll get the answer. 33600. Okay, and I get my answer to be 80 newtons. Sometimes before I put it into the calculator, I'll try and get rid of some of the zeros. There's 3 zeros here and 3 zeros here that I can get rid of. So I can just do this calculation, which makes it a little bit easier. Okay, use the physics equation sheet to answer these questions. Write the equation that links distance traveled, speed, and time. Speed equals distance over time. Distance traveled, therefore, equals speed times by time. It's already on the equation sheet. It looks like that on the equation sheet, so it's really easy. Then it asks, or it tells you the distance of the London Marathon is 42,000 meters. We knew that because it was on the previous question. And the winning time for the race was 5,600 seconds. Calculate the average speed of the winner of the race. We need to calculate speed. So we can rearrange this equation from here to make speed the subject. Speed is equal to distance traveled divided by time. There is a way you can do this without doing this rearranging first, but the rearranging has to be done at some point. So what should we do? We should do speed, which is equal to the distance traveled in this case is 42,000, so it's 42,000 divided by time, which is 5,600, which gives you an answer of 7.5 meters per second. Well, how would I have, and that's the answer. How would I have done that if I didn't rearrange first? Instead, I put the numbers into the equation first. Well, I would use this equation. Distance traveled is equal to speed times by time. And I will say 42,000 is equal to speed times by 5,600. To make speed the subject, I have to get this 5,600 and divide it by 5,600 on this side, and therefore divide by 5,600 on this side, and these cancel out, and then speed is equal to 42,000 divided by 5,600. Look at that, and that gets you the same answer, which is 7.5 meters per second. Superb. Final question. Explain why the speed of a competitor changes. Why the speed of a competitor changes during the race. Why do they speed up or slow down? All right. There's a lot of reasons why. So we have to break it down. There's two levels to this question. The first level is if you've said the relevant points and there are attempts for logical thinking, you get 1 or 2 marks. But that means your answer was never perfect in the first place. Level 2 says you've identified the relevant points, given detail, and logically linked to form a clear account. Clear account means a clear recollection of what is right in this question. And therefore, you'll get 3 or 4 marks. And 4 marks is the full marks. So, what do we need to say? The effect of the speed must be consistent with the cause of the change. So we need to state a point, and then you need to say what effect this speed, what effect this would have on the speed. I'll read the mark scheme out for you. It says competitors accelerate at the start. So they never start off at the same speed. They accelerate at the beginning. So what's the effect of the speed? So speed increases. Yeah, obviously. So at the beginning they speed up. The road's not flat, so the speed increases going downhill and decreases going uphill. Okay. When they go around a bend, their speed decreases, but they're accelerating around the bend. Okay. They could accelerate around the bend as well, even. Their tires might, sorry, not the tires might, they might tire towards the end, so they slow down. Towards the end, they're tired, so they slow down. They might get to the end and decide to make a sprint for it, so they might speed up. They might get a puncture, which means they would have to stop. And the resistive forces on the competitors may increase or decrease, so their speed might decrease or increase. Loads of things to say, but I'll probably just pick 3 or 4. I'll say at the start, they accelerate. So what's the result of that? So speed increases. Then I might say road isn't flat. Is not flat. Flat. Speed increases downhill. Decreases uphill. Then the next thing to say is they may have sections where they sprint, and if they sprint, speed increases. That could be at the end or in the middle. They might get a flat tire. Or a puncture. Oops, wrong color scheme. Flat tire. If they get a flat tire, what happens to their speed? They stop. Alright, there's a lot more things that you could say, but these are some things that might get you the marks. So, that brings us to the end, and therefore, some of you will have done really well. Congratulations. Some of you might not have done as well, so use this as an opportunity to go back to the correct question and fix it. Mark your work really neatly, because this gives you an accurate or really good representation of where you are at. So if you need to go back to any of the topics and revise it again, you'll be able to do that. Do not be disheartened if you didn't do well. Make sure you work on your maths, because in your physics paper that's one of the main things. So I'll see you in the next one.